3.1, certainly you must use the definition of derivative to find the answer to whatever problem it is.
Wait, hold on.
The definition of derivative I have given to you on the exam, so I'm starting to like you a little bit. 3.2. Anything beyond question 1, you will be taking derivatives in the standard way. You will not be using limit definition beyond number 1. Number 1 is limit definition. All right, so 3.2, 3.3.
You said standard.
Just standard rules we've been using the whole time. Everything we do normally we take derivatives now.
Okay.
Just
You said
that's number 1 only.
Yeah, that's
Yep, you got to use that definition number 1 only.
you said no limit definition.
No limit definition beyond number 1.
But
Number 1 only.
3.1 is.
Number 1 is limit definition. That is what it is. 3.2, 3.3 are just using standard rules of differentiation. Product quotient rule and sum difference rule, power rule, just the most standard problems in the face of the plan. Now, 3.4, you're going to evaluate a trigonometric limit. You're not going to take derivatives of trigonometric functions on the question of 3.4, so that will come from 7 through 14 specifically. Those are the only limit trig problems there are.
Wait, say it again?
In 3.4, the question is coming from 7 through 14, that type of question, where you're doing a limit that has trig functions in it. Not a derivative, but a limit. Right? But you have to relate the limit to the two limits
That you gave us.
that I gave you for that section, which are on page 155 at the top. Okay? Sin x on x goes to 1, cos x minus 1 on x goes to 0. Those are the two limits you need to be aware of, and you need to algebraically relate your question to those to solve it. Using L'Hopital's rule will gain you nothing in that problem. The point is not to know L'Hopital's rule, the point is to understand algebraically how these limits are related to the other known limits. Alright, so that would be a 3.4 question, is a trigonometric limit, not a trigonometric derivative. 3.5, it's going to be a position velocity acceleration problem. 3.6, what's that? 3.5, position velocity acceleration problem. 3.6, which is the main thing in that section. 3.6, just a chain rule. Just do a chain rule, man. Right? Sure you can do a chain rule. 3.7, you got to do something implicitly. It's coming from 11 through 26. I'm not that concerned about inverse trigonometric functions. I'm sorry, I lied. Sorry, wrong section. I was thinking wrong. 3.8 is log and exponential functions. You better know how to take the derivative. You need to be able to do a logarithmic differentiation problem. That technique we showed, logarithmic differentiation, right? Which is basically the question is 43 through 50 in that section. Not so many to choose from, so you should practice them hard and know how to crush any one of them. So it's going to be a logarithmic differentiation technique. 3.9, as opposed to having you show that you know the formulas for inverse trig functions, I'm going to have you do a problem related to the more general case, which we discussed last time, derivative of any inverse function. Okay, so 31 through 42. You know your x naught, y naught, E granola, right, that one. That's right. 31 through 42 in section 3.9.
So the derivative of any what?
Of any inverse function, which is 31 through 42. Which was the E granola, establish what x naught, y naught is, that whole slew. 310, what we just did, you should expect something within the first 31 problems.
Really?
It's one of those. It's 1 through 30. It's 1 through 31 somewhere.
31.
1 through 31 somewhere.
Could you go over
X naught, y naught stuff? Why not? Do an online one? Do an online homework question from there? What's x naught, y naught?
No, the hardest section so far for me is 3.2.
310? Yeah, I told you guys it'd be hard. That's why I left it just for one class.
Like, just the fact that it has weights.
So what's that? This. Raj, any questions from 3.9? What is it? What's that? What number?
No, not just in general, just explaining the, general, really on the back part of the
Here, this one. That's the standard. We'll use this example to explain it. Can you see it, or does it glare too bad? Yeah, you want some ambiance?
Oh yeah, I was gonna think of going on the
Well, we'll. Still, we can dim the lights a little bit. Is that better?
I think it might just have bad light.
How's that?
That's good.
I remember these moments in high school. Teacher would start running a film, actual film, like, right, a film reel. I used to watch the real thing, right?
Oh.
You guys watch this electronic junk. I watched real stuff. Lights would go dim, my eyes would blur, start snoring, slobbering. They'd wake me up, hit me in the face, go to the principal's office, call my parents.
For what?
My parents would whip me. Go to my room, blistered and beaten from the day. Go back to school the next day. Pray they don't turn on the lights again. Those are some good times. All right, so we were supposed to find the derivative of f inverse, it says. But we have the original function, f of x. And you're not going to be able to find the inverse of x cubed plus x minus 2. I don't even think you can. So x cubed plus x minus 2. So what I want to find is f inverse derivative, they put in parentheses, that's fine, at 8. So that means what I need is 1 over the original function's inverse,
Oh,
but at what value? What was that? At 8?
That's what you wrote.
that's what it says up there.
Yep.
No, that's not what I put here though. I want to know the inverse function derivative at 8. That's what they're telling me right. That's what it says.
Yeah.
Don't you have to solve?
But I gotta know what the original, this is just regular prime, this is just regular function. I gotta know what this is.
Don't you have to set it equal to 8?
Right. I'm gonna set equal to 8. Okay? X cubed plus x minus 2 equals 8. Why? Because in this notation, this is y naught for this function, right? Remember the formula is f inverse derivative at y naught is 1 over f prime at x naught, where x naught, y naught is on f, is on the regular function, not the inverse function. Okay? That's the formula. Which means that y naught, x naught, if we use this notation, is on f inverse. So, Rosales is correct. We need to set our function, that thing which contains the x values, equal to its y value, right? 8 is a y value for the original function.